Aidan Boyd, who's the main author, the first author, and the architect of the method, is traveling right now. So there are some days when advisors need to present students' work. So I'm here. Thank you everyone who survived until so late, and especially colleagues from Europe, because it's almost midnight, I think, for you. So thanks again. If you look at the title, we have post-mortem iris recognition. So I'm really hoping that you will not have bad dreams after this presentation. It is a little bit different than regular iris recognition in a sense that we need special methods or special features of methods that we propose for post-mortem iris recognition. One of those is interpretability. Which is probably why I'm here in this workshop right now. So, so forensic colleagues who were interested in this, because several years ago we did research showing that post-mortem iris recognition is possible, which was kind of gruesome, but also inspiring. So we have approximately 3 weeks after that to still recognize a person using iris texture, and they said, that's great, folks, but we need something that is interpretable, because if we want to use it in forensic scenario, we need to understand what these methods actually are doing for us. So that brings us to this talk and this method, which proposes something that can be interpreted by humans. And if you know some maybe history of iris recognition, we had Arun Ross here in this workshop talking about other things, but Arun was working pretty actually extensively on interpretable iris recognition methods. I think almost 2 decades ago, he proposed some works related to using SIFT and SIRP, pretty generic computer vision key point detectors to find some key points in the iris and match them. And Pat Flynn from Notre Dame also proposed something like more than 1 decade ago based on biological features, which we call crypts. So this kind of works actually exist. It's nothing new in terms of proposing human interpretable iris recognition. The problem is that with post-mortem iris recognition, that we have a lot of deformations that make sometimes features like crypts invisible or destroyed. So we just started to look at these images and started to think what we can actually do to still offer some interpretable method, but also accurate in terms of automatic recognition. And we decided to actually ask humans to do this task for us. So from this motivation slide, I'm going to the solution slide in which I'm just summarizing what we did. So we decided to train. Of course, everyone is using deep learning right now, so we also use some deep learning solutions. We decided to ask humans to look at pairs of post-mortem iris images, tell us if it is the same person or not, and what is important, annotate for us features that were supporting their decision. So in this way, we are not tied to any biological features, which is maybe bad and good in a sense that people are completely unconstrained what kind of features they selected. If something looked similar for them and supported their decision, we just took it as, you know, as the response, as the ground truth. So that was one thing. The second thing that was quite important for us was just to avoid any assumptions that we usually do in iris recognition. So for instance, assumption that pupil is always circular is no longer valid for post-mortem iris recognition because of deformations. Irises can be really rotated, like heavily rotated, because sometimes when these pictures are taken by technicians, they can even rotate the camera upside down, because this is how they approach cadavers. So again, this problem is a little bit different. So we asked humans. They were not experts. We had many different experiments related to post-mortem iris recognition, but getting actually annotations and decisions from human experts is quite hard, because we don't have that many experts in iris recognition. We have some of them, but the pool of experts is not that drastically huge, which is different for fingerprints, for instance, or even for face. So we ran an experiment using Amazon Mechanical Turk. So the workers actually were definitely not iris recognition experts, but they did actually pretty good job. So in this slide, you can see an example window from the tool that we created. You have a pair of iris images, both are post-mortem, and we ask them to tell us if it is the same iris or not, and annotate features and match them, connect them, features that were important for them to make this decision. It was a little bit more complex than this. So we wanted to increase the quality of these annotations and increase the quality of decisions, just to gather the information, the most valuable information for us. So to be more specific, I should say that we follow the WACV protocol, which is quite popular in fingerprint recognition. WACV stands for analysis, comparison, evaluation, and verification. So it's a sequential algorithm in which two independent experts are used to finally judge about the similarity of fingerprints. And this can be, of course, applied to other biometric methods. So what we did, we just had the first subject, the first Amazon Mechanical Turker, looking at the pair of iris images, and they were providing the judgment and also annotations. And then we had another person who had the previous decision and previous annotations, and we asked that person, what do you think? Here is what the previous subject was thinking about this pair of iris images, and here are the annotations, and this is what you see on the right, top right corner. And then the question was, okay, now what do you think? What do you agree with that person or disagree? Independently of agreement or disagreement, please annotate for us features that were supporting your decision. And that was actually a good move, because we had a little bit higher accuracy in this two-stage scenario. So the overall performance was 61-ish%, which is not actually great, but we should also take into account that these pairs were pretty challenging and these people were not experts. So at least we had 60% of correctly classified and correctly annotated data. Okay, so what we did next? The next thing, this slide is quite busy, but what is actually important here is that we only took genuine pairs that were correctly classified by subjects. So we didn't want to take any incorrectly classified or incorrectly annotated pairs. We just wanted to take only the data that was correctly classified by all the subjects, especially because they were not experts in this task. So we took all the annotations that were supporting people who correctly solved this task. There were some subtle things that we had to apply. For instance, we had multiple people looking at the same pair of iris images. So some of the features which were annotated by them were overlapping. So we had to come up with some approach how to deal with this overlapping regions. So we just decided to take the largest feature if we had multiple features annotated in the same place. Irises were segmented automatically and cropped to 256 by 256 pixel resolution, which is kind of arbitrary, but it was actually well aligned with ISO standards, so we should be good here in terms of the recognition. And we ended up with 700 images, which is not actually that huge amount of data, which is also good because it shows that we don't need a huge amount of data to actually make it work. So what we have annotations from people who did it correctly. And what we want to have right now, of course, is some automatic method that will first detect the features. We do not name these features. As I said in previous work, we could have, for instance, scripts, or we could have other anatomical features of irises. Here, we don't name them. So in some sense, they are I don't want to say black boxes because we want to talk about human interpretable methods, but these features, we can think about these features that these are places in iris image that are in some sense interesting or important when the matching is being done. So this detection that you can see here on the right, which was done by the model that we trained using the human annotation data. MaskRCNN is pretty standard deep learning based segmenter. Of course, we could use any other segmenter here, but actually MaskRCNN did a pretty good job. So what you can see here are the automatic detections of different features in genuine iris pair and imposter iris pair. Again, we can't name them, so we don't know if it is crypt or other feature, but it could instruct the forensic examiner whose task is to compare this iris image pair that there's something interesting happening in this place, right? So it's like supporting the human, telling, hey, look at this place, look at this place, look at this place, because these are features that are human-like, and other humans who are looking at these pictures consider these features as important. So that's the first part, the first step, feature detector, and then the feature descriptor. The question is how to encode these irregular areas and how to match them. And we decided to use or reuse our previous work in which we proposed binary features. So filtering, as John Dugman did almost 3 decades ago. But this filtering is not with Gabor wavelets, which is a standard approach in iris recognition. This filtering is done with human-sourced filters. So that was a previous experiment in which we also asked humans to look at iris image pairs. We used eye tracking device to look where they were looking, and then we trained special filters that were derived from human-sourced iris patches. But the pipeline, the idea is exactly the same as in classical iris recognition. So we take this patch, we filter this iris patch using several different kernels, and we encode this as a binary code. So instead of having the binary code for the whole iris, we have binary code for each feature, each detected feature that you can see on the left in this picture. So because we have these features, binary features for each patch, this is actually the origin of the name of this method, patch-based matching. So we can calculate the distance, and because again it's binary encoding, we can use the Hamming distance. So what we are doing, we're trying to detect how many features correspond to each other. So we can, of course, think about different approaches. What does it mean that the feature match? And we just decided to use those features that are more or less geometrically aligned. So we are assuming that this irises are more or less aligned. And then if we have a feature that matches another one that is geometrically in a completely different place, we just consider this as a non-match. So after this step, we're calculating the Hamming distance patch by patch, so pair by pair, and average the Hamming distance for the top n matching pairs. And this n is one of the hyperparameters of this method. In this case, we just decided to use 5, the highest, the most matching pairs. So what we have right now is, as you can see on the right, we have the detections using MaskRCNN. So these are some patches, some areas that can be helpful for a human examiner when they are doing some independent comparison of iris image pairs. That's the first thing. The second thing, we have these blue lines connect the pairs, the patches that match, given, of course, this method. So it's another perhaps helpful information for a human. Hey, here's the feature, but actually these features do not match, and these features match. So maybe this is something useful, and you should look actually at these 2 places, because maybe it will help you to make your decision. As you can see, it's different for genuine pair and it's different for imposter pair. And especially for imposter pair, number of matching pairs is, of course, lower. Some of them that are matched are in different places. So that could be also an information for a human examiner that something maybe is not correct here. So maybe it's not actually the genuine pair. So in addition to this, we have, of course, the comparison score based on this 5 most matching pairs. So we can also, in addition to offering some interpretable result, we can also use this in automatic iris recognition as any other method. And one of the questions is, of course, how this method compares to other methods, because we know that there's usually a trade-off. So if we want to make the method human interpretable, we usually are getting a bit lower comparison accuracy when compared to other methods that are not necessarily human interpretable. So we selected a bunch of methods, iris recognition methods that we have right now. Actually, this is not the whole list. I think we have probably approximately 20-ish methods that we can use right now, different open source methods. But we selected a few of them, and one is deep learning based that is specifically created for post-mortem iris recognition. WACV is a popular commercial iris recognition tool. This is from our friends from the University of Salzburg, developed several years ago. There's another method that we create for just post-mortem iris recognition. We also use the SIFT, just a classical approach, how we can build the human interpretable iris recognition method. And CRIPS, this is from Professor Flynn. That was almost 10 years ago. So a few RSC curves. And actually, when I saw these RSC curves, I was positively surprised because I was expecting that this method, of course, will offer some human interpretable results, but it will be terrible in terms of the accuracy. But it's actually not that terrible. First of all, the best method the best on the database that we had at hand was this human interpretable or human sourced binary statistical image features, which we designed several years ago. But this is not human interpretable. It follows John Dagman's pipeline, uses different kernels, but it's really hard to actually interpret the result. We have the Hamming distance as the for matching score, and that's it. So this is not what we want. And the second method, which was pretty good, was based on SIFT. And you can say, hey, so maybe it doesn't make sense to make this effort and ask humans to annotate something for us. Just use SIFT. The problem is, if you look at this method, this 128 is the number of SIFT features, SIFT key points that we need to achieve this accuracy, which is a lot. So imagine that you have 128 points in one image and 128 points in another image, and a lot of actually lines connecting this pairs. So I'm not sure if this is really human interpretable and what's the value of this. So what we did, we just decided to use only 10 features, which was aligned with our method, and the accuracy of the method that is using only 10 key points as our method was definitely lower than this. So this patch-based matching was marginally worse than this, but it outperformed the WACV method, which was super surprising. One thing maybe I should mention is that WACV is a very good commercial matcher, but probably it never saw any post-mortem iris images. So it was designed for live iris images. I'm not super actually surprised now when I think about this. It was a little bit worse than the method that was trained on post-mortem iris images. So I think I don't want to take more of your time. So what is actually interesting from this work is that you can propose a relatively simple method, because if you look at the pipeline, it's just the difference between the classic iris recognition method is that it's using only several parts of the iris texture or iris annulus. So we are limiting the amount of information that we use for matching. And that creates human interpretable method, which is nice, which, as I said, I was expecting that the accuracy will be much worse, but the entropy and the amount of information, identity information that we have in iris texture is so rich that we still can actually use this limited number of amount of information to propose something that is competing in terms of accuracy, but it's offering human interpretability, which is actually great accomplishment or great signal that there's a lot of information that we can actually use in iris. What else? I think if you wanted to try this method, it should work well not only on post-mortem iris images, it should work also on live iris images. It's not limited to post-mortem iris images. We created a GitHub repo and everything should be there. If you have any, of course, questions, just let me or Aidan or other colleagues know. And I think that's it.